Welcome, everyone. Welcome to our field trip series. And today we're going to be talking about Mars 2020 for the American Museum of Natural History. I'm Carter Emart, and I'm the director of astrovisualization, and we're thrilled to be doing this today as part of our Mars Fest overall celebration. In about 18 hours, or just a little after, Mars Perseverance rover is due to lift off from Kennedy Space Center in Florida, if all goes well. And today we have a very special program with a very special scientist who's going to lead you through what Perseverance rover is going to be looking for on Mars. In our field trip series, we're proud to feature our software OpenSpace. It's a NASA-supported, freely available open source software. And our pilot today, as usual, is Micah Echinopura. And so, Micah, I'd like to introduce you and so we say a few words.
Hi, okay. Hi, everyone. It's Micah here. Glad to be piloting for you today. We're going to have a cool show and we're going to go to Mars. It's going to look really awesome. So happy to be here with you guys.
Well, this particular oh boy, having a lawnmower go by. Pardon me. We're all home. We're all in this together, of course. So today's guest is Bethany Ehlmann, and she is a research scientist at NASA's Jet Propulsion Laboratory, JPL. She's also a professor of planetary science at Caltech, the California Institute of Technology. And Bethany has been on a number of missions at JPL of current and previous Mars missions, including the previous Spirit and Opportunity solar power rovers. And we just sort of lost Opportunity about 2 years ago in a global dust storm, being solar powered. But she's also an active scientist with the Curiosity rover currently on Mars. And that she is also on the Mars Reconnaissance Orbiter, and she's heading up a mission to come, the Lunar Trailblazer Orbiter mission. So this is very exciting. Bethany also has a children's book with National Geographic, and it's entitled Dr. E's. Dr. E, just lost my notes because someone was calling. Here we go. Dr. E's Superstellar Solar System. And so I hope she might talk a little bit about that. But she will be taking questions on our chat, but we're going to save those for the end because she has a lot to present today. She also proposed the Jezero crater for Mars 2020 rover. And pardon the interruption. And the last point I want to make is that she's one of the scientists attached specifically to the Mastcam Z camera on board Perseverance, as well as the Sherlock instrument on the robotic arm. So Bethany, it's wonderful to have you. Please take it away. Thank you.
All right, well, thank you, Carter, for that introduction. It's wonderful to be here at the American Museum for Natural History, sharing for you the excitement of Mars 2020, which set your alarms because it's scheduled to launch out of Cape Canaveral tomorrow. The launch window opens at 7:45 a.m. Eastern tomorrow, 7:45 Eastern. And so if the weather is good, that this rover will be on its way to Mars. So I'm very excited to share with you a bit about the science that we'll do and the landing site. So thanks, Micah, for navigating. And if we want to start here at the beginning, we can start on Earth. And those of you who are stargazers or in a place where the night sky is dark enough can catch Mars, somewhere in the sky field. Actually, it's actually in the southeast of the sky between midnight and dawn right now, a bright red dot in the sky. What's been so remarkable, though, is that we have been able to journey to Mars, and we can start that journey here virtually in open space. We've been able to journey to Mars over the years via our spacecraft. And so this process of exploring Mars, we haven't sent humans yet, but the process of sending robots to Mars began in the 60s with the Mariner spacecraft, followed by Viking. And as we zoom into Mars, you're seeing Mars as it would have looked to Viking, approaching, those first orbiters with their high resolution imagers here. So you can see, Mars silhouetted here partially against the sun. So we're now going to take off the solar viewing portion and go straight to Mars as we have it here. And we're zooming in. And the first thing that you can see, and we can start Mars to rotate around, but the first thing that you see is that Mars is a heavily cratered surface. That means the surface is ancient, similar to the moon in that way, that we have land on the surface of Mars that has been there for 3 or 4 billion years, so heavily cratered terrain. What you see coming into view now is terrain that's less cratered. Fewer craters means younger, and you can see there's an enormous volcano, Olympus Mons, that has produced recent lavas. We continue to spin around Mars, come into view. Mars, like Earth, has enormous icy polar caps, water ice at the poles, trapped, frozen there today. And you can see that beautiful cap with the seasonal layers of water ice around it as captured by Viking. So if we start to head back down here to the younger Martian terrains near the volcanoes, you can see there are a few more. There's on the Tharsis Plateau hosts Olympus Mons volcano, as well as 3 other large volcanoes. And then you can also see this enormous gash in the surface, which is the striking Valles Marineris canyon system that slices across the equator. It's a fracture, a fault, a large fault-controlled canyon in the crust of Mars. Now, if we pause kind of around this vicinity for a while, let me get your eye in. In addition to that gash, you can hopefully see there are some streamers coming off of it, heading to the north or the upper part of this image. What these are some of the most striking features that were seen by Viking. These are enormous channels. Now Mike is gonna help you see this better by flipping from what we see with our eyes with the visual imagery captured from Viking to a laser altimeter map collected from our orbiters that shows the topography. So here blue is low, red is high, and you can see how these spectacular channels drain out to the northern lowlands of Mars. Now, this looks like for all the world, there should have been an ocean here, right? And, suggestively colored blue. So we have these outflow channels of water thought to be formed by floods that catastrophically carved these about 3 billion years ago. And maybe at one time, filled these northern lowlands with a body of water that would have been, equivalent to the Gulf of Mexico in terms of its size, a large ocean. And so I'm going to leave you with that, and we're going to now talk a little bit about what we know about Mars in a slide pack here to share with you some of the results from prior exploration before we come back to talk about specifically what Mars 2020 will do. So one of the things I mentioned is that Mars is cold today, polar caps, just like Earth. What you're seeing here is one of the first images from the surface of Mars from the Viking missions of the 70s. This was a spectacular mission, landing a 1-ton vehicle on the surface of Mars in the 70s. This is hard today, and so this was a great accomplishment for NASA. One of the cool things you can see amid there's some landing hardware on the side. A piece of the landing system is actually off there in the Mars landingscape. That's the cylindrical tube. It sort of fell off when Viking landed. But that white material you see is actually surface frost. So Mars, like Earth, has approximately it's a 24-hour, 40-minute day. It has 4 seasons, but the average surface and the max surface temperature gets to 30 degrees Fahrenheit, but the minimum surface temperature gets to minus 200 degrees Fahrenheit. So it is cold on Mars. It is cold at night. It is cold at the poles. And one of the things we see in the morning, though, is this frosty ice. It's also dry, and so we don't actually have liquid water on the surface today. But we saw those channels, right? So 3.5 billion years ago, we did. And the big question is, well, what did Mars look like during that early period? That's the period when we have the first signs of fossils and fossil life on Earth. So what did Mars look like during its watery, wet time? And then why did it change? What happened, right? These are the big questions and part of the reason we explore Mars. And fortunately, over the last decades, we have had a flotilla of exploration that we've been able to accomplish. So this chart shows the successes and failures over the years, starting with the Mariner and Viking missions. So everywhere it's gold, a space agency successfully made it to Mars. And you can see the golden age of the first golden age was the 1970s of exploration, culminating in Viking. Then there was a dry spell. Funding for NASA planetary missions dried up, but it got re-excited and re-engaged in the late 90s. And you can see that we've sent a number of rovers, some of which I've had the privilege to work on in the past. Right now, Curiosity and Mars Insight are still roving and landed on the surface of Mars. And right now, every orbiter from Mars Odyssey onward is still there in Mars orbit. So we have a flotilla of 6 around Mars, and not just NASA, but the European Space Agency and India as well. 2020 is a big year for Mars. Some of you may be aware that the United Arab Emirates is joining the Mars party, launching the HOPE orbiter about 10 days ago. Tianwen-1 is China's first mission to Mars. They also have launched, and tomorrow, 7:45 a.m., Perseverance, if the weather is good. So let's talk about now what this flotilla has brought us in terms of knowledge. If we go to the movie, so you all, if we start that, so you all flew into Mars, right? And we're going to continue to fly into Mars, but I'm going to talk about a different type of data. We ended with topography or altimetry data from lasers. Here I'm going to talk to you. One of the things we've been able to do is to get better and better pictures of the surface of Mars that let people like me, a geologist, get up close and personal with the rocks of Mars and really tease out those details. Some of you may have been to the Grand Canyon or gone for hikes in the mountains where you get spectacular rocks. So we're zooming here at progressively higher resolutions of images, but you'll notice this image has added color. Now, Mars is not blue nor yellow, but what I'm showing here are the signatures of minerals that are detected with spectra in the infrared that allow us to not only get these amazing images at high resolution where you can see the details of what's in the rock layer, but we can actually also tell what those rocks are made of. And so we ended the video here with this sort of spectacular image where if you just look with a little geological intuition, you can kind of tell what's on top of what, right? There's this lower rough with these ridged units that are blue. Blue here means clay minerals that formed from water, and they're especially enriched in those ridges. Then on top of it is this yellow unit with carbonate and olivine, other water formed and igneous, and then water formed minerals. And then on top of it, just igneous rocks are in purple. So there's this layer stratigraphy that we can read the record through time. And if we go to the next slide, this particular slice of time, what we're showing is actually a slice through the crust of Mars, where those ridges that you're seeing with clay minerals formed from water are actually the conduits of a Martian groundwater plumbing system. So, you know, you can imagine Mars warm and wet with the water flowing on the surface, just like it's shown here. But there's also these underground conduits and reservoirs flowing that all of which could be habitats for potential life. So if we go to the next slide, there are a few places, and I was just the place that the tiny, 1 kilometer by 1 kilometer area I was just showing you is more or less where the green arrow is on this map. Now, the details of this map are unimportant. It's basically a plan view map of Mars, and everywhere there's a dot of different color is a different type of mineral that formed from water. You can see that there are thousands of places that we can go to understand the history of water on Mars. If you go to the next slide, what you'll see is that we only get, with our landers and our rovers, we only get a few opportunities so far to explore these dots on the map. I, as a geologist, want to go to all of them, and I hope that we send more robots, we send humans, and we get to explore more. But I'm going to just share with you a little bit about what we found so far. And Mars 2020 is actually going near the arrow, near the green arrow. So let's talk about what we found. With the Spirit rover, we landed in Gusev crater, drove around, and one of the most exciting things we found was in this feature called home plate, which is this light tone rock that for all the world, it looks like you could kind of slide into home plate there, kind of baseball analogy style. What we found that home plate was made of were these rough rocks that were 90% silica opaline silica, which is actually important because it indicates an environment like what's on the next slide here, which is an environment where you have warm waters that are saturated and coming up through the surface in these volcanic terrains and then precipitating out the minerals that they carry. So this is a hydrothermal system in Iceland, but this is probably what the surface of Gusev crater at that particular point on Mars looked like about 3 billion years ago. Similarly, if we continue onward our tour, the Opportunity rover landed in a vast plain of sandstone. So these are rocks that are comprised primarily of sand-sized grains. So imagine, you know, your playground sand just gets cemented over time. All right, what we saw when we drove up to these sandstones was that they actually had these sulfate salts that formed in acid conditions. They also had a bunch of iron oxides, and most of them represent sand dunes. So like you might see in a desert, sand dunes cemented with time. Some of the layers here are sand dunes. But what was in the slide in the corner there were little ripple marks where you have evidence of shallow waters. And the environment would have looked something like this. This is from Western Australia, where we have seasonal acid lakes in the arid environment. If we go to the next slide, one of the third kind of big rover was Curiosity at Gale Crater. And here, what we have are these very fine layers of clay-bearing rock. This is something, if you stick a core in the bottom of a lake and you pull it up, that is what you will see in most of the muddy lakes around New York and elsewhere. You'll see these very fine layers that are laid down each season, formed from liquid water. So we found this with Curiosity, and the scene would have looked something like, on the next slide, what we see in areas with fluctuating water tables, where it moves up and down, up and down, up and down each season. So lakes that come and lakes that go. If we go to the next slide, what we then can do at each of these sites, one of the key questions is, okay, water. So water in hydrothermal systems, water in acid shallow lakes, water underground, water in deeper lakes that come and go seasonally. These are great habitats for life, but was life there? Okay, so how do we get at that question? We know that Mars once hosted habitats, was warm and wet at about the same time Earth had its first life. Now the question is, how do we figure out whether it was inhabited? So on that slide, what we can do is we can look at rocks, and we can do that with rovers, but then some of the other detailed measurements, isotopes, details of organics and organic chemistry, biominerals that occur on a nanometer scale, we need to go to the lab to do that. We can't do that on a rover. So if we go to the next slide, we are starting right now, and we means the NASA, the broader scientific, we are starting a campaign of sample return, of which the Perseverance rover that is launching out of Cape Canaveral is the first step. So Perseverance will explore Mars and collect the best samples to bring them back to Earth as part of a 3-set mission of sample collection, launching those samples off Mars, and then delivering them back to Earth. Continuing onward, so the Perseverance is equipped with a suite of instruments that enable this: cameras, a coring caching system, which I'll talk about in a moment, and then a suite of instruments. I'm just going to hit the highlights because I could give a whole talk on that, but you want to see Mars eventually, and we're going to get back there. So if we go to the next, the key aspect that makes the Perseverance rover different from Curiosity is its coring and caching samples. So not only can we drill into Mars, but we collect that sample. It's about the size of a piece of chalk. And then we load it into a sample tube that will eventually be put in a canister to be brought back to Earth. Some of the key features that we have on Mars 2020 that enable us to pick the best samples are instruments that let us see at a tens of micrometer scale microscopic images of the rock and then what the rock is made of. So these multicolors here are tracing water-related minerals and the presence of organic matter, so carbon, like we are made of carbon. So tracing this with the Mars 2020 instruments Sherlock and Pixel, which are on the arm and are deployed on rocks. Mars 2020 also has a subsurface radar that allows us to see beneath the surface as well. So Mars 2020, as it goes, not only will we see what's on the surface like past rovers, but we'll also be sending pulses down to see what lies beneath. And finally, if all of that weren't enough, Mars 2020 also has a Mars helicopter. So this will be the first, if successful, this is a technology demonstration. If successful, this will be the first time that flight on another planet is demonstrated. So just think about the Wright brothers in the early 1900s and how far we have come from then if we can start flying on another planet. Pretty cool. So with that, we're going to go back to open space and get our own bird's eye view of what lies ahead for the Mars 2020 rover. But before I do that, I think Carter has an announcement just for anyone who may have joined midstream.
Yeah, thank you, Bethany. And this is fascinating. And it's this thorough walkthrough of the mission. It's very exciting. I just want to remind us all, and if some of you just joined, what we're looking at is Dr. Bethany Ehlmann from NASA's Jet Propulsion Laboratory in Caltech. She is a science team member on Perseverance, which is headed toward Mars tomorrow. And we're looking at this with OpenSpace. If you're interested in this software to examine Mars up close and personal, you can download it yourself at openspaceproject.com. We have a live chat with scientists and a curator from our museum, Dr. Denton Abel, our curator of meteorites, and graduate student Marina Gemma, and also astrophysicist Jackie Faherty, who are taking questions. Also, please write your questions in, and we'll take a few for Professor Ehlmann when we finish up. But Micah Achimapura is flying us in open space, so we're going to come in close. So thanks again, Bethany.
All right. So continuing our tour, we have now, Micah has rotated Mars so that we've switched from the outflow channels to near the Mars 2020 landing site. But I first want to give a little intro. So what you're looking at, right, you can see this big hole in the ground. That is a large 1,900 kilometer impact crater. So that's like almost half of the continental US size impact crater. That's a bad day. But fortunately, that bad day was 4 billion years ago. The Isidis impact formed, setting the rocks around the landing site. And then about 500 million years later, some lava flows came over top of that. And you can see those Syrtis Major lava flows. Just one second. So I have a power issue with my computer, which is of unclear origin, which is going to make this real interesting. Yeah, Micah, we're going to have to figure out what the backup strategy is when I lose power, because Yep. Okay, so why don't you say that I'm switching over to phone, and then this is going to be real interesting.
We're working through a few technical details with Professor Bethany Ehlmann from NASA, and so she's going to be picking up on another device to continue her talk. We're pleased to bring you OpenSpace. It's NASA supported from the Science Mission Directorate, and so we're part of what they call their Science Activation Group, bringing you educational materials to communicate science to the public. So I think we're about to, well, perhaps it'll take a moment or two more for Professor Ehlmann. Yeah, and perhaps there is a question, and so I'm just trying to see if we have that. Well, let's see. Kenneth asks, can you explain what biominerals are? This is a good question, and for Professor Ehlmann when she comes back. Let's see. Okay. So let's see. I might take another question just while we're at it. Francisco asks, if you had to bet between Mars and Europa to have signs of life, which would you choose? Now, that's a good question. The question deals with Europa, which is the second moon out of the 4 large Galilean moons that Galileo saw 400 years ago. around Jupiter. And that moon is, we actually know from the Galileo mission that it has an ocean of water underneath its very cold icy crust. And there are volcanoes on the inner moon, Io. So the next moon out is Europa. So where there's liquid water, well, we know that water is common to all earthbound life, that there's a chance possibly that water being there. In the case of Mars, we can see that it was Earth-like billions of years ago, at around the same time that life on Earth evolved. So if we had to bet, well, maybe I'd place my bet where water is today, maybe out at Europa. The Europa Clipper mission is being designed right now at NASA's Jet Propulsion Laboratory, and is a very exciting upcoming mission. So is Bethany back? Not quite yet. So let me see if I might take another question. Dan asks, does Mars have tectonic plates? If not, does that play a part in why it's now dormant? Well, yes. Mars is half the size of Earth, and Mars and Earth are both still cooling off from the formation of them, and so Earth still has enough heat in it that our crust is broken into plates, and these are these tectonic plates that move around the sort of continental drift, so that we can see that North and South America sort of fit together with Africa and Europe, or did in the past, a few 100 million years ago. In the case of Mars, volcanoes, and it was cooling off, and so you see these volcanoes in the thick cracks of Valles Marineris. I think Bethany is coming back, so we're almost ready to go back. But
yeah, I think I'm back. I'm on my phone. I don't know if you can hear me.
Wonderful, Bethany. Thanks for coming. Thanks for joining us back in.
Yeah, we planned for all contingencies, except for this was the moment that my power supply cable stopped working. So keeping it interesting. Should we resume our tour?
Yes, please, Daphne. That would be wonderful. We're looking forward to getting up close and personal to the landing site.
Okay, so we're gonna continue our tour, and you'll have to bear with me because I will not be able to see the screen extremely well. But Micah, you've got the slide and Zoom here, so I can follow, and I know the YouTube will follow that. So we're picking it up here with the CTX coming on top of the image. So what you were looking at, right, is the impact basin of Isidis and the lavas coming up, 3 billion years later. We're going to zoom into the CTX image of Mars, and we're going to move closer here. So the CTX is a 5 meter per pixel scale set of images that were acquired of Mars and then mosaicked by a team of folks to make these beautiful images of the landing site. So as we keep zooming in, some of the things that you should notice are the rough cratered terrains toward the upper parts of the image. And there's Jezero crater, is that 45-kilometer crater that's sort of near the center of the image. Something that you can notice on the lower left is tongues of lava that are trying to make their way to Jezero but never quite made it. One of the things now, as Micah zooms into Jezero, that you should immediately notice is that Jezero is not a pristine crater. It has been eroded, and there are 2 channels going in and 1 channel going out. And you might be able to see those, discern those on the screen. If we just flip on our guide image here, Micah, the graphic 2, or graphic 3, I think. If we just let's show the Jezero chart. So if we look at the Jezero image here, what you can see is that's been drawn up by my colleague Caleb Fassett, that there were 2 channels flowing in and 1 channel flowing out, and they've formed these spectacular fan deposits or deltas that we're going to be visiting. And the other thing is that this lake, when it was full, when water was flowing in and out, was 2 kilometers, 2,000 meters deep. This was a deep lake, deeper than Lake Baikal. Those of you who are trivia buffs might know is the deepest lake on Earth. So what's cool about this, if we go back to the stratigraphy image, is that we have this lake that was there 3 billion years ago. So if we go to the stratigraphy image, what we're going to be exploring in the lake is the upper part of deposits that were laid down 3 billion years ago when Mars had water. But what's cool is what's being eroded is what lies beneath. 4 billion-year-old rocks that were similar to what I showed at the beginning of this talk that preserve this ancient groundwater system. Those pieces of that system are what has been flushed into Jezero. So we kind of have 2 opportunities to explore ancient habitats on Mars. If we continue our tour, zooming in, one of the things you'll see now is that beautiful fan or delta start to come into view. So what is a fan? What is a delta? Well, it forms when water flowing at high velocity into a basin hits a basin, velocity slows, and then the sediments are deposited, spanning outward. Now, this was deposited into a lake, but the analogy for Earth, deltas also form in oceans and gulfs. The Mississippi River Delta, and Michael will put that on, you can see is quite similar in form. It's that splay out of sediments as a river hits a basin and deposits everything it's carried, being those rock fragments or organic molecules from life. So what we're able to see also is we're able to see the composition of this delta, and we'll just flip on that CRISM image briefly. And what you'll see is that there are different kinds of rocks at our Mars 2020 landing site. There are red rocks that signify the igneous mineral olivine. There are purple rocks that also signal volcanic type sediments. And then there are green materials. The green materials are the clays and the carbonates that formed from water. So this is all very exciting to a geologist, because this is a great place to both look for life and understand past Mars environments. So let's put on the landing ellipse here. And this is basically the location where Mars 2020 is going to be targeting for landing. So we can start our tour. We're going to just pick one spot and guess one spot where Mars 2020 might land, and then take you on some stops of what we will be exploring with the rover. So Micah can zoom us in and in spectacular detail. And Micah, I'll ask you to flag me when we kind of get to some of the locations I want to show, because I'm not able to follow in the same way I would be if I were on my computer. Okay, perfect. So what we're doing here is we're now zooming in to the high-rise image, and one of the things that we want to do. So, I'm a geologist. Stratigraphy, what rock layers on top of rock, is something that's important to geologists for tracing through the history. One of the things we'll do is we will either land right on the delta itself, or we'll land on the crater floor. And if we land on the crater floor, what you're able to see in the high rise that Micah is showing are these this really cool dark cap rock that we don't quite know what it is. It's like made out of volcanic minerals, but we actually don't know if it's a lava or a sandstone of sediments. So that cap rock is there, and it covers up these fractured sediments that have clays and carbonates and are probably the lake bottom. And then those are covered by sand dunes that the rover is going to have to actually try to avoid. It's like a little bit of a Martian obstacle course as we try to explore these cool features. So that'll be one of the first things we see, is that we check out the sediments at the bottom of the lake. Then what we'll do is the rover will start to swing around and actually explore the delta itself. So these water deposited sediments. And we will be swinging around to the front of the delta. And Micah can tell you. Yeah, so we're hitting a nice side view where we're able to see layers in the delta. So what you'll see is different bright, dark tone layers. That's because over time, building up one layer of rock, one layer of sediment after the other, and we can see those organic materials. Perhaps we'll find them in some of these layers. So that will be like the second thing the rover will be really looking for, is tracing the history of water through time. The next thing that we'll do is then we'll, after exploring that, is we'll swing up onto the delta itself, and we'll go near the impact craters here, and we'll be exploring the upper surface of the delta. And one of the spectacular features, and some of you I think will be able to pick this out, there's these curved features that are called scroll bars that are in the upper surface of the delta. If you imagine a river snaking its course through a landscape, these are those deposits preserved over time for us to be able to explore. So once we've done that, the rover is looking for life, looking for evidence of organics the whole time. And once we've done that, we'll be swinging then out toward the edges of this delta deposit to some of the terrain that has the highest signature of carbonate. This it's like a MgCO3. Those of you who are chemical formula aficionados, MgCO3, magnesium carbonate, which is one of the richest deposits of carbonate on Mars. And carbonate is important because, number one, it signals neutral to alkaline water, and number two, it acts to seal in and preserve fossils. So if there are fossils, it's a great place to look. And Micah can flip on the CRISM image of this rough surface at the edge, this margin of the lake where we see these carbonates, and you can see this bright green color indicates that they're super enriched in this particular location. And so with that, JESRO's exploration of Mars 2020 will be complete, but there's more because we can keep going out of the crater rim and toward the rover will have this time cached a collection of samples. And by this time, we will be able to, we'll be carrying probably at least 20 samples, or we will have placed them safely in the JESRO ellipse in a location for a future rover. But we'll have done our caching activities, selecting the best rocks for return to Earth. And then we'll be able to go to the more ancient terrain where there's another safe place for the future FETCH rover to land. And as we go in this location, you can see beautiful hills, this eroded landscape. These are some of the oldest rocks on Mars. They're 4 billion years old, formed after that Isidis impact. And one of the things that you can see just south of the landing ellipse, it's a little hard in these images, but just south of the landing ellipse, you can see these beautiful fractures from that groundwater system plumbing that are 4 billion years old that would have been great habitats to search for life. So that's the like long-term extreme goal for Curiosity would be this site-to-site traverse. But the heart of the mission, the first couple years, we will be spending in JESRO crater and doing our sample collection. So Micah, when you're ready and you think we've hit a good point, we can transition back to the slides for just 3 slides, and then we'll take some questions shortly. So to finish up the talk, so we're at the deposits now with the fractures, and you can see, yeah, these are the fractures that I was talking about that have the groundwater related systems, and that dashed area there is where it would be safe for a future rover to come rendezvous with Perseverance and pick up the samples for return to Earth. And so when we finish, then we will have this beautiful collection of rocks that record 1 billion years of the history of Mars, and maybe we'll have evidence of fossils. If we keep going, what Micah, is the other slide up? I'm sorry. Okay, so right, as to remind you, what I'm seeing, Micah, is the open space right now in the Zoom. So what this is part of, right? Reminder, we're doing this for both in situ exploration and our campaign of sample return. And this is, if we go to the next slide, this is, and this is the mission slide, Micah. All right, so one of the things we'll be able to do, of course, is investigate these samples to search for potential biominerals that would be minerals formed uniquely from life in patterns, and responding to the question that Carter was taking. To look for those at nanometer scale will require those samples in the lab at Earth. And in terms of future missions, the outlook ahead is rich for Mars. So I mentioned there are 3 missions going in 2020. There's another mission, Europe. The European Space Agency is sending a rover in 2022. And then NASA plans in 2026 to start that process of bringing back the samples that Perseverance will have collected. So as we finish this, I'll finish it with the view of potentially human geologists on the surface of Mars one day, looking at these rocks. I hope that some of you, and especially, I'd love to go to Mars, but I hope that some of you and some of especially the kids who are listening on the line, those of you who are in school right now, you may be this person who is gazing at this rock actually on the surface of Mars, continuing our exploration for the future. And so if we go to the final slide, I'll end it there. And I am very happy to take any further questions in the time that we have available.
Well, wonderful, and thank you, Bethany. This has been a wonderful presentation. I know we've had some technical difficulties. And one of the questions I thought was a great question, is from 7-year-old Nate. And Nate asks, will we need to use nuclear propulsion to get to Mars?
Yeah, it's a good question. To get to Mars, we don't need to use nuclear propulsion. And in fact, the launch that will be happening is a standard chemical propulsion rocket. So it takes about 7 months to get to Mars if you launch at the optimal time, which is why we want to hit this launch window, because otherwise it can take like 2 years to get to Mars. So we need to hit this launch window that goes from tomorrow until August 15th. And then it takes 7 months via traditional chemical propulsion, and that's totally fine. Now, the aspect of nuclear propulsion is this rocket is, the rover itself is actually nuclear powered. It uses a thermogenic radioisotope source, which basically means that it has a set of radioisotopes that decay and let off heat, and that heat is used to power the rover. And that's what allows Perseverance to have a suite of science instruments and to have a very long-lived mission, because this gives us more power than solar power alone.
Well, thanks. And part of that answer, Bethany, Lisa Marie had asked how long it takes to get there, but there are 2 good questions. These are great, from Dan and from Grace. And it's about, so how stressful is it to drive a rover on Mars? And the sort of corollary to that is, do people at NASA drive the rover, or is it programmed to drive itself?
Great questions. Okay, so I tell people that as a scientist, I'm a rover backseat driver. I'm not the rover driver. There are actually folks with degrees that are mostly in computer science and electrical and mechanical and electrical engineering who tend to serve as the rover drivers, although anyone can actually be trained to do so. Basically, it's programming the rover. Because Mars and Earth are far enough apart, we don't actually like joystick the rover, because even at their closest approach, it still takes about 10 minutes for light to go back and forth. So if you were joysticking it, you would joystick it, and then 10 minutes there, 10 minutes back before you could joystick again with the next move. So that is very inefficient. So we don't do that. So instead, what we do is we program sequences of rover activity over time. You basically get a 3D view of Mars. You know what the timing is, and you plot out points, X, Y, Z points, 3-dimensional space points that you want the rover to traverse. That's the most efficient mode of driving. The rover also has some smarts, or some pre-programming to it, that it also can pick routes that are safe by using computer vision and using its stereo eyes to calculate on the fly, actually maps of the topography and the roughness. So if you set a point, if the rover driver sets a point, the rover can also, albeit more slowly because it's doing all these calculations, the rover can also make itself to that point, avoiding any obstacles.
Well, Bethany, thank you. And that brings up this point of optical navigation, even in the landing on this one. It's quite sophisticated, really amazing engineering, and we hope that Perseverance has a safe journey to Mars. So I want to thank you. And I also want to point out that in our live chat, you can follow a survey link, which we hope you'll fill out, as well as want to point out that this evening we have a comedy night on Zoom. You can go through the live chat to register for that, but it is a 18+ event. So just wanted to say that. But this has been a wonderful opportunity to get the science from Dr. Ellman. And it's just been a pleasure to have you here. And so thank you all for joining us here on Field Trip Mars 2020.
And watch the launch, 7:45 Eastern tomorrow. Thanks, everyone. And thank you, Micah, for driving.
Thank you, Mike.